All right, that's last right. Thank you for joining, everyone. We'll start off with a question, who am I? This is not an existential crisis that I'm having. It's more really a case of, how do you know who I am? Now, you can look there, you see my name is on that slide, but then I created this slide. That's me claiming that. That's me putting that claim there. I wrote it on my badge here as well, but then I did that. I'm sure you probably trust the organisers here that they know what they're doing, so they didn't get some imposter in to give a talk. So you have some trust there, but it's not a very strong claim about who I am. And I've got a title there. I've said I'm a CEO. Again, I've chosen this myself. If you look back at my website over a few years, you'll see that I used to call myself Grand Vizier. I used to give myself different titles. I say to my employees that they can really give themselves whatever title they like. Thankfully, so far, they've not come up with anything too outlandish. But again, it is something that they've chosen themselves, and I've chosen this myself. It's a claim I've made about myself and about my role. More evidence. I've got a website which gives some details about my company. Well, really, I suppose this is just the fact that I've got a slide that shows a website, but let's believe that I've got a website. Really, all that shows is that I control the DNS entry about this website. But again, you can trust various things here, and you're probably going to do that and believe some of the information that is on here. And why not? One of the things, if you read some of the things we do, right at the bottom there, we say we do security audits. So we take code, smart contracts that people have written, say DeFi projects, and we audit that for security. We produce a report there, and then investors will take those reports and read them and decide maybe whether they want to invest in this project, whatever risks there are involved there. And those investors are trusting that my company here has some integrity, has some competence, and particularly is not colluding with the project that we're auditing and just agreeing that they're a safe project when maybe they're a rug pull or a scam or something like that. So in all of this, there's a lot of trust involved and not much really concrete mathematical claims is what I'm really aiming for. Okay, other points while we're on this slide, and what I'm going to talk about today particularly are zero-knowledge proofs. We do run courses around zero-knowledge proofs. If you're interested in these, please do contact me. These are, if you're a developer, these are free for developers to join, and we love people to get involved. We love sharing our passion for this area of technology. Okay. So what I'm going to talk about. Some of the background technology, aspects of zero-knowledge proofs that are pertinent to oracles. I'm going to talk a little bit about DIDs as well, because we're interested in identities. Some of the challenges that there are to using these technologies along with oracles. And then I'll go through some of the solutions I've come across. I'll have to say my slides are not great, so I'll probably digress somewhat from these and probably rush through the latter few slides, so we have more time for Q&A, which is going to be more interesting. Okay, so let's start with zero-knowledge proofs. You probably all have come across this term. You may know something about it already. The essence of a zero-knowledge proof is that we have a prover. They're going to show that they have knowledge of some private data to a verifier, and they do that without revealing what that data is. It also may be used to show the correctness of some arbitrary computation. Now, what would be ideal if we're talking about oracles is if we had a prover could prove to a verifier that a data came from a particular source, and we could prove some statements about that data, prove some statements about the integrity of that data, but maybe we could also keep that secret or keep some privacy about that data as well. So really that's the ideal that we may be aiming for, but we're a long way from that yet. I should say as well that zero-knowledge proofs are it's a bit of a buzzword or buzz phrase. They're not a magic bullet. People often sort of use them. They have a problem, they say, okay, we'll throw zero-knowledge proofs at it, that will solve it, in the same way that they say this about machine learning and things like that. They're not a magic bullet. They won't solve every problem, but they are incredible things. Some people see them as quite magical, and if you go into what they do, they can seem quite magical at times. I got on the slide there the ability to prove the correctness of arbitrary computation. If you're old enough, you may remember the Hitchhiker's Guide to the Galaxy, and in that there was a computer called Deep Thought who was asked to solve the question of life, the universe, and everything, and took, I think, millions of years to do this. And it came up with the answer 42. And the people were quite taken aback at this answer and asked the computer if he was sure that this was correct. And the computer said, yes, I'm sure, I've checked it. Now, that book was written before zero-knowledge proofs were invented. If it was written today, what you could say instead was that the computer could also give a zero-knowledge proof of that computation. And then the people wouldn't have to ask the computer whether it was sure that that answer was correct. They could run this proof, they could verify this proof, and within a couple of seconds, they could see whether this computation was correct or not. And this, to me, is one of the really magical things about zero-knowledge proofs, is that they can take an incredibly complex or long-running calculation or computation and give a proof that the answer of that computation is indeed correct, and that can be verified very, very quickly. The other aspect that they can do is the zero-knowledge aspect, and this is the idea that when you verify a zero-knowledge proof, you only really get one piece of information back. You only get one bit back, and that's whether the proof is correct or not. You don't get any other information if it's truly a zero-knowledge proof, so you don't find out what a secret was if the secret information was involved in that proof. And those two aspects are often used. Sometimes you don't need both of those aspects when you're using zero-knowledge proofs. When we use them, for example, in scalability solutions, we're more interested in proving the correctness of computation rather than in trying to have any kind of secret data there. But both of those aspects can be done with zero-knowledge proofs. One of the problems that I've found with them is that if we're thinking about oracles, is there's a bit of a chicken and egg situation in that the zero-knowledge proof requires data inputs. You can have some private data inputs, some secrets, and you can have some public data. But then that really infers the existence of some oracle to provide that data. And so what I'm trying to do is to try and get the zero-knowledge proof sort of jammed into the oracle, but then really the zero-knowledge proof is asking for data as well, and it's difficult to kind of do that without getting sort of kind of recursive situation. In terms of where we are with this technology, they were invented back in the 80s, and they took a while to take off, and they really came into their own maybe 2015, 2016, that sort of time, when they became very practical. And at the moment, there's kind of maybe two main types of zero-knowledge proof. We have things called snarks, ZK snarks, and ZK starks. And these are two different approaches to providing a proof, but they essentially do the same thing. Snarks were invented first, and they have the advantage that the proof you create is small. It's around 250 bytes. So incredible that you can get proof of a large computation into just such a small piece of data. But that's what snarks do, and they are very quick to verify. The verification time for a snark is linear on the size of the computation that happens. And it's because of this that we can put them into smart contracts. So you can supply a proof to a smart contract, allow that smart contract to verify the proof, and you know it's going to always take the same time no matter how complex the original thing is that you're trying to verify. Starks are a more recent invention. They do work quite differently. They they're more flexible in some ways. They don't require as much setup as we need in snarks. They're also quantum resistant, so the underlying cryptography they depend upon, they really just need some agreement around some hash function, and that is quantum resistance. And I know quantum computers are always around 10 years away, but maybe one day that 10-year will be here, and then we will be more reliant on stocks than we are on snarks. Okay, let's talk a little bit about DIDs. Now, there was a great panel yesterday, I hope you saw that, with people talking about DIDs, and those people know a great deal more than me about it, so please do go talk to them, go talk to people like Civic about this. A way of creating identities, it's a standard that has been done. This is an example of what they can look like. They can apply to people or to things. I think they have great potential. I have found that maybe we're still not quite there with them, and there's still a lot of work needs to be done to use them. But I think they do have a lot of potential. One of the problems that I think was certainly mentioned yesterday was around GDPR and how if we're storing information that these DIDs relate to, information about identity, how do we do that in a way that will comply with regulation like GDPR? Associated with these identities are some claims, so verifiable credentials. And these are things that are certainly better than the claims I was making earlier on. So my claim about who I am, just because my name's on a slide, well, better than that would be if I had a credential to show that. Typically, you have a wallet which holds your DID, and you use that to collect some verifiable credentials. Which will show some credential that you own that is associated with that identity. The one problem really, I suppose, when we're talking about oracles here is that these credentials really, again, assume that there is some organization or some oracle providing that credential. So maybe if you want a credential about your identity, you'll be looking at the passport office, or maybe you'd want some credential from a bank, but you're reliant upon this organization, this bank, to be providing that credential. Of course, you can do some self-attestation, like I did with writing my name on the slide, but then the problem with that is, who's going to believe that? Maybe you'll be more inclined to believe a bank. And one of the aspects of around verifiable credentials, something that we want, is the idea of selective disclosure. So if I want to prove, for example, that I have a certain amount of money in my bank account so that I can pay my rent, I would like to be able to do that without disclosing any other information about myself. I don't need to tell you my gender to be able to do that, or my marital status, or anything like that. Really, I just need to be able to show maybe that I've got a bank account or I have a certain amount of money. So selective disclosure is a very useful thing if we can achieve that. And then unlinkability. The people who are providing these credentials, sadly, they could be nasty people. They could get together, they could collude, and start to infer information about the people that they have issued the credentials for, and start to infer information that weren't part of those credentials, but that have come out because they've colluded, and they can work out that information. So that's something we would like to avoid. One area where zero-knowledge proofs have been quite successful in terms of privacy has been with tokens and privacy-preserving tokens. For example, Zcash. I'm sure you all know Zcash, but there are other ones, Monero and Grano, and all those ones. And these have worked very well, and I think they've worked particularly well because they have been quite limited in scope. They know what they want to do, and they have done that. The way they have worked, the advantage that they have over maybe other tokens is that if you think about a public blockchain like Bitcoin or Ethereum, what they rely on is they want to show the correctness of some transactions. So there are nodes that are collecting transactions and verifying these transactions. You can go away if you want and collect all the transactions from Bitcoin and go through every single one and check that they all add up. if you want to do that, of course. And that's really the essence of what the blockchains are trying to do. But in doing that, what these public blockchains have done is to make public all the other information that's in that transaction. And you don't need both pieces there. You're really concerned with just the correctness of this transaction. And so what Zcash managed to do was to separate that out and say, well, what we can do is we can create a proof that a particular transaction is correct. But we're not going to give you any other information about that. So we're not going to tell you which address that transaction came from, who the coins went to, how many coins were involved. We're just going to show that that transaction was correct. And that's all that you really need to know to have confidence that this system is working correctly. And they did that by a mixture of zero-knowledge proofs and various other bits of cryptography, and did it very, very successfully. And yeah, so it's a limited disclosure there of the correctness of the transactions. So if we want to use this technology with oracles, we have some challenges. Some of the approaches that have been taken have need specialist hardware. So we have things like trusted execution environments needed. And what these allow you to do is they allow you to prove some computation and do that without giving away extra information. So they have extra cryptography built into the hardware that allows you to verify that a certain computation is being done correctly. But it is a requirement. There's an additional burden if you want to have this involved. Incentivization, obviously, we always have to be thinking about this. If we want people to adopt solutions that we are producing, we need to be sure that the incentives are aligned. We need to be sure that there is a good reason for them to adopt it, and them to use our solutions, that there are good reasons for us to produce them. It would be very nice if we could generalize these types of solutions across different types of data feeds and processors. I really liked the talk on, I think it was the first day, where they were talking about very generalized and very complex oracles. I think it was from UMA. They were saying about these human optimistic oracles and the idea that we're not, we can go beyond just supplying a price feed, and then we can give information about very complex things in the real world. And that would be great if we could have those types of things as oracles and be able to verify the information back. But to do that is quite a challenge, to be able to do that in a generalized way. Another challenge, if you're looking at the incentives and also malicious behavior, is what happens if people who are involved in the oracles or in providing data have nothing at stake? What prevents them from behaving maliciously? Reputation systems can help with this, and then if we talk about identity systems, they can help prevent Sybil attacks. There's something of a trade-off here. If we talk about decentralized identifiers, one of the advantages with those is that we can create multiple identities, and that can be very useful, and for humans it may be something very desirable. But then, of course, we don't want people to go overboard with that and then just have a huge amount of identities and do Sybil attacks with those. Something that I've heard mentioned a few times is user experience. I'm sure you'll all agree, just generally in crypto, we do this fairly badly. We're still, I always think that some of the software we produce, it's written by developers for developers. We're obviously very excited about this whole area, and we forget that other people aren't as maybe as excited and don't know the technology and don't want to know the technology. And often the user experience for this is quite poor. And then something I've already mentioned, I think that if you're making some attestation about some fact, either you're acting as an oracle, and maybe you're an organisation that is well known, in which case people will perhaps may believe you, but perhaps you don't want that. Maybe you would want anonymous attestations to be taken into account. But then, how can we be sure about the credibility there as well? And just thinking about some of the areas that this may be used in, we perhaps have been focusing, and I think particularly in this conference, we tend to focus on things like DeFi and finance. One of the areas I think I use as my litmus test for this is the idea of, it's an idea in blockchain of whether we could do this with healthcare. It's a really tough nut to crack, and I think if we have solutions in healthcare, then we've pretty much gone there. But I think at the moment, we're really concerned with DeFi so far. Okay. Let me rush on. I'll just go quickly through some projects. I'll talk about some experiments that we've been doing. This is not a product that we've built. It's really just something we're playing with, some ideas. But maybe it'll introduce some nice ideas for you and show you the types of things. So the idea behind this, the blue nodes here, they're meant to be oracles, and they produce some zero-knowledge proofs. We'll say they're going to use Starks. That some computation has been done correctly. So the oracle is taking some data and it is doing some computation with that data, maybe aggregating a price, maybe reducing, getting rid of outliers, etc. And we can produce a proof that has been done correctly and then pass that on. A nice idea that Solana came up with is proof of history, and we can use this as a kind of a clock on blockchains, a decentralized clock, and it allows us to timestamp data. VRFs, verifiable random functions, another aspect of cryptography. These allow us to pick actors within a blockchain and do it in a random way, do it in a fair way, and be able to prove that that has been done in a random way. So we could use that to produce, to check, get which oracle we want to use, and get that to provide the data. And then an idea I tend to like when I'm thinking about blockchains is the idea of honeypots. So putting in something that is going to be there to pick up bad actors, to pick up malicious behavior. And this could potentially help with OEV as well. So oracle extractable value, the idea that oracles are very powerful, they can use that to their own advantage and make money by the fact that they have control over information. Maybe we could proactively look for people who are doing malicious things, and then maybe if they have a stake, we could slash the stake or do other kind of behavior. Okay, I think I'm going to be running out of time, so I'll just quickly go on. The idea that we had was that this network would then push data onto a layer 2, and the proof would be pushed onto layer 2, and then something like Starknet as a layer 2 could then put proofs onto layer 1 as well. One of the projects that seems to have made some progress in this area, Deco, they have some means of really getting some servers and doing some cryptography to allow these to be used as oracles and provide proofs for that, but in a way that doesn't rely on extra hardware and isn't too intrusive on the existing website. I won't go into the details. I'm running out of time. There's other ones I think you probably know. Town Crier. Delegatee are more involved with sharing of credentials. Teller I don't want to talk about because Teller are here and they can do this much better than I can. So please go talk to them. Semaphore, they're a way of showing membership of a group, and that's like quite a nice quite a nice primitive, I think, that we could use and build into other systems. And Chainlink are obviously doing quite a lot and allowing other systems to integrate with them and introducing hybrid smart contracts to allow off-chain things as well. There's a quick comparison of their approaches. I won't go through that. Conclusions, still a long way to go, but I think this technology certainly could be useful. If you want more information, please do get in touch with us. There's a link there to the slides. It's still early days for all this, but certainly lots of potential. And I think one of the aspects that's going to be easier is, in terms of the zero-knowledge part, certainly, is the proof of computation. The privacy part, I think, is a much tougher nut to crack. So that's my talk. Thank you, everyone, for listening, and please do ask questions if you have them.